I'm more or less been talking.
All right, let's open up to page 75. For those of us that were not here on Friday, we missed you, okay? But we did go through on to the next section. And in this section, we're specifically looking at a continuous graph versus discontinuous. Okay, some terminology might be a little bit new for us. We're basically trying to figure out if we cannot draw a graph without lifting up our pencil, okay, it's not smooth or whatever, we're trying to figure out where on the graph, if we do have to pick up our pencil, what does it look like? And we were basically looking at two different types where we could have some type of jump going on, like two sides do not meet up, or maybe we have some type of hole, okay, just a little piece of our graph that was kind of removed from the picture. So on Friday, we took a look at those two different types. Now for today, we're going to get into a little bit more of the algebra part of determining this on page 75, but you still need to be able to look at page 74. So make sure we can see both of those pages at the same time. Okay? Now on Friday, if we take a look at f of x, which on page 74 was the first graph, the top left-hand corner, what did we classify as the discontinuity, and where did that happen? Did we label something as a jump or a hole? Where did we sit? Go ahead, Jack. Jump at x equals 3. Okay, so if you take a look on page 74, and if you were to go to the x value of 3, notice how the left-hand side and the right-hand side are not connected. Okay, they do not meet up. That's what we classify as a jump. Okay, there's some type of gap between the two sides. Okay, so what we're going to try to do today is transition away from just looking at a graph to determine what's going on, because I know that's kind of easy for us. We can look at a picture, but we're going to get into the algebra behind it. Like, how can we just take a look at the equation? So if we continue just look at the graph for a little bit, notice how at this x location of 3, we had two open circles, okay, meaning there's no defined point at that spot. There's no closed circle to actually count. So this next question is asking us, is there a defined point on that graph? We'll just say no, because there's no closed circle. The next thing we really want to pay close attention to is, where is this special spot on the graph where one equation is ending and the next one's beginning? Okay, because that's where these discontinuities can happen. And if you take a look at the equation for f of x, notice how the first equation ends at an x value of 3, whereas the second equation begins at the x value of 3. So that's kind of where we're interested. Okay, if one ends and one begins, do they meet up or do they not meet up? Okay, causing that jump. So we'll go ahead and label those as 3. Okay, where does one equation end and the next one begin? Graphically, we're going to try to determine what the left side and the right side of 3 are doing. Okay, that's what the little negative and plus mean from the left and from the right. So on the graph, if you were to trace from the left-hand side of 3, notice how you'd be getting closer to that open circle, and that open circle has a height of 2. Okay, that's your y value. It's getting closer to a height of 2. The right-hand side of 3, if you look at the graph and you were to trace it, is getting closer to a height of 4. Okay, so we'll say these are heights, or y values. So notice how this is kind of cluing us into that we have a jump going on. If the left height is 2 and the right height is 4, clearly those are not matching up. Okay, those are different heights. There's going to be a gap between them. That's kind of signifying our jump. Now I know we can figure these out based off the graph. What we are going to try to do today is try to get the same results but based off the equation. Okay, we're going to pretend that the graph isn't there just for a second. So let's see if we can get the same numbers. As x approaches 3 from the left, okay, we're going to take a look on page 74. Again, we're going to pretend that the graph isn't there. Okay? Take a look at the equations. Which one should we use to represent the left side of 4? Oh, sorry, the left side of 3. My bad. What do you think, Caitlin? How'd you know? There we go. X is less than 3. X value is to the left of 3. So we're going to go ahead and write down that equation. X, or absolute value of x plus 3 minus 4. So if this is the equation that shows up on the left-hand side, we want to see what this equation is doing at this x spot where it ends. Okay, what height does the graph have when it ends at this value of 3? So we're going to go ahead and plug in that 3 to see what we get as our height. So 3 plus 3 is 6. Absolute value doesn't change anything. Minus 4, we get 2. Okay, so notice how it matches what we saw on the graph. So we don't necessarily need a graph every single time to figure out these values. Let's check out the right-hand side. So as x approaches 3 from the right, if you look at the equation on page 74, that would be the second option. Okay, x value is bigger than 3. So if this equation begins at the x value of 3, we want to see what the height is at that spot. So we'll plug in 3. We'll get negative 1 plus 5, which is 4. Okay, so notice how it matches what we said based off the graph. This is going to help us practice, get used to not having the graph there to actually determine the heights. Okay, we can just use the equations. So far, so good. Let's try g of x. So on page 74, that's the next one on the right-hand side. On Friday, what did we say was our discontinuity and where did it happen? Good, Caitlin? All right, x equals negative 3. So on page 74, x value of negative 3. Notice how where one graph ends and the next one begins, there's a gap between them. Okay, that's our jump. The next question is, do we have a defined point somewhere at that spot? Yeah, we have that closed circle. Okay, so yes, we do have a defined point, and the y value, if you look on your graph, is negative 2. Okay, so in the last example, it was a jump, but it did not have a closed circle somewhere. This one is also a jump, and it does have a closed circle. Okay, so sometimes you'll have one, sometimes you don't. It all depends on the graph that you have. Based on the equation, where is this special spot where one equation is ending and the next one's beginning? Can you tell with how it's written on page 74? What do you think, Hadley? Good. That's where the first one ends and the next one begins. Okay, so negative 3 is found within both of those domains or constraints. So that's our special spot of interest. That's what we want to kind of analyze here. Now graphically, let's see what the left and the right-hand side are doing. So at this spot of negative 3, okay, that's where one equation ends and the next one begins. If you trace the left-hand side, you get closer to the closed circle, which has a height of negative 2. Okay, so that's from the left. And as you trace the right-hand side, you get closer to the open circle, which has a height of negative 4. Okay, again, these are y values, these are heights, so notice how they're not matching up. Okay, they're different from each other. Let's just practice and see if we can get the same results based off the equations. Okay, so pretend the graph isn't there. As x approaches negative 3 from the left, okay, take a look at your equations. The one that shows up for values smaller than negative 3 would be the first one. Okay, so if the first equation ends at negative 3, we want to see what is the height it has when it's ending. We'll plug in that negative 3 and see what we get. So 3 squared, 9. Negative up front would be negative 9. Plus 7 would be negative 2. Okay, checks out what we had from the graph. Let's see the right-hand side of negative 3. So looking at the equations, numbers bigger than -3, that would be the square root equation. So if this equation is beginning at -3, we want to check out the height it has when it begins. So we'll plug in -3, we'll get 0 minus 4 would be -4. Okay, checks out what we had based off the graph. But eventually we're going to get away from the graph. How are we doing so far? Okay, let's go ahead and try the next few. So h of x at the bottom. On Friday, what did we say we had as our discontinuity? Yeah.
Whole of -1.
Whole at -1. Okay, so graphically, take a look at the x value of -1. Notice how the left side and the right side do meet. Okay, there's no gap between them. And they specifically meet at an open circle. Okay, that's our whole. It's a chunk missing out of the graph. So whole at -1. Do we have a closed circle somewhere else at that spot? No. Okay, it's just that open circle. Based off the equation, where's this special spot where the one piece is ending and the new one's beginning? -1, good. All right, so let's see what's happening at this spot of -1 on the graph. We want to trace the left-hand side and the right-hand side. So here's -1. As we trace from the left, we get closer to the open circle, which has a height of 1. And if we trace from the right-hand side, which would be on the parabola, we also get close to that open circle, which still has a height of 1. So unlike the jump, where we had two different heights, notice how for a whole, they do have the same height. And that kind of makes sense off of our definition from Friday, where we had two sides meeting, but at an open circle. Okay, so the heights should be the same. Let's see if we can get the same result from the equation. So we're going to approach -1 from the left, again, pretending the graph isn't there. We're going to see if we can still get the same numbers. So based off the equation, from the left, that would be the absolute value. And if we plug in -1, we'll get 3 minus 2, which would be 1. All right, checks out. Let's approach -1 from the right. So based off the equation, that would be our parabola. All right, let's see what height this one has as it begins. So -1 minus 1 would be -2. Square it, you get 4. Negative out front becomes -4. Plus 5, we get 1. All right, so they're checking out. All right, let's try our last one, p of x. What discontinuity did we have and where was it? From Friday. Go ahead, Hadley. Whole at x equals -3. All right, so on page 74, there's a graph of p of x. X equals -3. Notice how the left side and the right side do meet at an open circle. Okay, that's our definition of a whole. Is there a closed circle somewhere else, though? Yeah, what's the y value? Y equals, good, Caitlin? -2, good. Okay, so just like the jump, sometimes you can have a closed circle, sometimes you might not. Okay, we have the same thing going on here, but it still fits the definition of the discontinuity. Okay, we have both sides meeting at an open circle. We just have a closed circle somewhere else. Okay, still fits the definition. Based off the equation for p of x, looks kind of confusing because there's 3 parts, but all 3 of them somehow begin and end at -3. So that's our special spot that we kind of want to analyze. So let's check out -3 from the left and the right. As we come in from the left-hand side, we get closer to the open circle, which has a height of 2. And as we come in from the right-hand side, we still get closer to that open circle, which has a height of 2. Okay, notice how both sides have the same height. So they should be meeting up. Let's see if we can get the same results based off the equation. Alright, so we want to choose the correct one from the left-hand side of negative 3. Those would be x values smaller than negative 3. So that would be our first one because it says less than 3. Let's see, if we plug in negative 3, we'll get 2. Okay, checks out from what we saw in the graph. Let's check out the right-hand side. X value is bigger than negative 3. That would be the absolute value equation. And if we plug in negative 3, minus 1 would be negative 4. Absolute value changes it to positive 4. Minus 2, we get 2. Alright, so checks out what we saw in the graph. So what we have here is a method that we can use without a graph, okay, no picture necessary, to help us figure out what's happening at these piecewise interesting locations. Okay, do they meet up perfectly? Do we have a gap going on? What the heck does it look like? Okay, no graph necessary because now we can just look at the equations. What we're going to do though before we start to get to some examples that don't have equations are taking a look at the vocabulary a little bit more. So for those of you that weren't here on Friday, this might be a good kind of review. On Friday, we said our definition of continuity, like being able to draw a graph without lifting up your pencil, was if you had two sides, okay, the left and the right, meeting at a closed circle, okay, some actual defined point there. Because if you think about drawing that graph without lifting up your pencil, we can go from the left to the right, no problem. Okay, there's closed circles or a graph at every single point. So continuity we're going to describe is a graph that has the left and right sides meeting at a closed circle at the location of x equals a. So whatever special spot you have on the graph. Sometimes we said it was -1, sometimes we said it was -3. Okay, wherever one equation ends and the other one begins, that's kind of our location we want to analyze. Okay, do the left and the right sides meet at a closed circle? Okay, basically everything has the same height. Everything's meeting up. If one of these two things is not happening, for instance, if they don't meet up, that means they have some type of jump or gap. But if they do meet up at an open circle, that would be our point or our whole discontinuity. So if one part of this definition doesn't really fit or doesn't seem to work, it must be one of these other two options. So for a jump discontinuity, we've kind of seen two examples. Sometimes you can have a closed circle somewhere. Okay, sometimes you don't. Okay, the point doesn't really matter. It's all about that gap between the sides. So we'll say as a definition, the left and right heights or y values, whatever term you want to use, are different. Okay, there's a gap or a jump between them because they don't have the same height. The other case would be maybe they do have the same height, okay, they do meet up, but unfortunately there's not a closed circle where they meet up. So that could look something like this. Maybe you do have a closed circle, but it's somewhere else, okay, not specifically where they meet up. So this is our whole. So in this case, we'll say the left and right heights meet at an open circle. So for some reason, if our graph is not continuous, they don't meet at a closed circle, these are your two options of what could be happening. And we're going to try to determine if it is one of these two, which one is it? Okay, no graph. Are we ready to try just an equation? We're going to step it up, okay? Let's try it. So the first thing we have to do for 1 is try to determine where is this special spot on the graph that we want to test. Okay, where do we want to check to see if they meet up or if they don't? Can we figure out that X location? What do you think, Blair? -1, good. Alicia, you were going to say the same thing? Yes. Perfect. Okay, so notice how that's where one equation ends and the other one begins based off the domains. So x equals -1. Okay, we want to test that spot. So let's see what the sides are doing. Okay, do they meet up? Are they different? We're going to see what the case is. So as x approaches -1, because that's our special spot, -1 from the left, we got to make sure we choose the correct equation. So that would be our first one based off of the inequality. If we were to plug in -1, we want to see what height the graph would have when it ends at this x location. So -1 plus 4 is 3, square it 9, negative out front, -9 plus 3, we get -6. Let's check out the right-hand side. That would be the absolute value. Let's plug in -1. Minus 3 would be -4. Absolute value changes to +4. Minus 10, we get -6. Okay? So at this point, okay, with these two things that we just discovered, can we conclude kind of what's happening at this spot of -1? Do we have a jump? Do we have a hole? Is it continuous? What do you think, Hadley? How did you know it was a hole? Okay, so at this point, notice how the left and the right side are meeting up. Okay, so they do have the same height, but we need to determine, do they meet up at an open circle or do they meet up at a closed circle? Okay, so right now we know they're meeting up. We just have to figure out what's going on when they meet up. So how do you think we can determine whether we have an open or a closed circle at the spot of -6? What do you think, Olivia? What's going on here? Yeah, take a look at the domain. There's no bar, right? You see how there's no equal bar under either of those? So will you ever have a defined point at -1? No. So between these two options, which is what the -6s were telling us, we can then look a little closer at this constraint or domain section to determine that there's no closed circle at this same height. So it has no choice but to be the hole that Hadley said earlier. So we'll say there's a hole at x equals -1. Okay, that special spot we had to test because the left and right sides meet at an open circle. Does that make sense? Okay, the -6s were telling us they do meet, but we have to figure out what do they meet at. Open circle, closed circle, there's a difference between the two. I like that so far. All right, let's try 2. Where's this special spot that we need to test? Where are we interested in analyzing kind of what's going on as one graph ends and the next one begins? Can we identify it? Hello.
Who wants the answers? Well, I wasn't saying I was going to give you. Are you prepared for Elgar to come in this week?
Not at all.
When's your prep?
I already had it. Second. Yeah.
I'll come down after class.
Okay, sounds good. Where's our special spot? Can we find it? Where's one equation ending and the next one beginning? Yeah? -1, good. Take a look at the domains. That's where the first one ends and the next one begins. Okay, so it happens to be the same as the last one. Let's check out the sides. Let's see, -1 from the left. That'll be our first equation. So as this first equation ends, we want to figure out the height that it has. So we'll plug in -1. Plus 3 is 2, times -2 is -4, plus 2, -2. Let's check out the height from the right-hand side. That would be the other equation. Plug in -1. Plus 3 is 2, minus 4 is -2. All right, so the heights on both sides are the same. Okay, they're going to meet up. The question is, what's happening where they meet? Do they meet at an open circle? Do they meet at a closed circle? There's a big difference between the two. What do you think, Julia? Why? There you go. If you take a look at the two pieces, okay, that -1s that we said we have to check out, notice how one of them has a bar. So you will be able to have a closed circle somewhere at this spot. Okay, so the left and the right are meeting at a closed circle. So notice how it fits our definition of continuity. The left and the right side meet at a closed circle. There's no hole, there's no jump. We'll say g of x is continuous at the x location of -1. That special spot way to check out. So even though we have one graph ending and the next one beginning, you'd be able to draw that idea, okay, that spot, without lifting up your pencil. There's no jump or there's no hole for you to kind of skip over. Okay, it's a continuous graph. Let's check out another one. We're going to step it up a bit. Where's our special spot? Where does one equation end and the next one begin? What do you think, Blake? We have 2 of them, right? All right, so if we have 3 pieces, notice how the first 2 begin and end at 3, but the next 2, okay, the middle and the third, begin and end at 5. So we actually have to check this twice, one for each of them. So maybe we'll separate that little box. Okay, x equals 3 and x equals 5. Let's check out 3 first. So as x approaches 3 from the left, we want to see what height the graph would have. So the left-hand side of 3 would be that line. If we plug in 3, we get 3. Let's check out the right-hand side of 3. That would be the parabola, the middle equation. If we plug in 3, we'll also get 3. All right, so the left height and the right height are both 3, so they're meeting up. We have to determine what is happening when they meet up. So these are our 2 options right now. Open circle, closed circle. We got to figure out which one it is. What do you think? What do you think, Caitlin? Okay, so if you check out your inequalities, notice how one of them had a bar. So you do have a closed circle somewhere at that spot. Okay, one of those heights is included. So it looks like our graph is continuous. We have the left and the right meeting at a closed circle. So h of x is continuous at x equals 3. Okay, the left and the right are meeting at that closed circle. You can draw it without lifting up your pencil. Nice, smooth, fluid graph. But now we have another spot we got to check. Okay, so the first one was good. Let's check out 5. So as x approaches 5 from the left, okay, so now we've got to take a look at other inequalities. to the left of 5 would be smaller than 5. That would be the middle equation. And if we plug in 5, we'll get 25 minus 10, which would be 15. Let's check out the right-hand side. That would be our absolute value. If we plug in 5, we'll get 2 plus 2, which is 4. So what's going on? The left-hand side, height of 15. Well, this way for you guys. Left-hand side, height of 15. Right-hand side, height of 4. What's that? That's a jump, right? They do not meet up. They have different heights. Okay, there's a gap between them. So we'll say jump at x equals 5 because the left and right heights or y values are different. Okay, they don't match up. Go ahead. How are we doing? Can we see the difference between our 3 scenarios? We have a jump, okay, y values are different. We have a hole, y values are the same, but we have an open circle. Okay, our definition of continuity, though, is that the heights are the same with a closed circle. So there's 3 things that can be happening where one graph ends and the other one begins. We hanging in there? Okay, we're going to stop there for today. I know we still have some time left, but this last one might take us a little bit, and I want to make sure we have the time to spend on it. In the meantime, though, maybe you want to try some of the homework problems. Okay, see how those go.